Welcome from Creative Learning Resources on the series How to Get a 7 in IB Chemistry. This video is on Topic 10 Organic Chemistry, Subtopic 10.1 Fundamentals of Organic Chemistry. The whole topic 10.1 will be fully covered in this video. Don't forget to watch 10.2 in order to fully understand the topic 10 organic chemistry. The HL students should watch the videos on topic 20, 20.1 and 20.2. Don't forget to make your own notes while watching the video, and after understanding the topic fully, do practice of solving the past papers using the classified booklet. So let's get started. Topic 10 Organic Chemistry is for standard level students. Subtopic 10.1 Fundamentals of Organic Chemistry. To start off with this topic, we are going to discuss the homologous series, which is a series of compounds of the same family with the same general formula, and each member of this family differs from the very next or previous member by a common structural unit. An example of the homologous series is alkanes. Alkanes are the hydrocarbons, means these are the compounds made up of hydrogen and carbon only. Hydrocarbons are the most simple type of organic compounds containing no any element other than carbon and hydrogen. The table is showing the number of possible carbon atoms in the hydrocarbons. As the number of carbon atoms increase, the number of hydrogen atoms also increase according to the general formula CnH2n plus 2. This general formula applies to all the alkanes where the N is representing the number of carbon atoms in the respective alkane. Let's say we have 4 carbon atoms, so by putting the number 4 in the formula, we can find out the number of hydrogen atoms in this alkane called as butane. So that's how the butane contains 10 hydrogen atoms in its molecule. All of the compounds shown in the extreme right column of this table are different alkanes. The difference of all these alkanes is in the number of carbon atoms present in them. Methane is a type of alkane which contains only 1 carbon atom and having 4 hydrogen atoms attached with it. This is its structural formula. Similarly, eth stands for 2, containing 2 carbon atoms, and the ane suffix is used for all alkanes. In order to draw ethane molecule, first of all draw 2 carbon atoms linking together with the single covalent bond, and then join 6 hydrogen atoms surrounding these 2 carbon atoms by single covalent bond. Similarly, propane contains 3 carbon atoms. Prop means 3 and ane means alkane. All anes mean they contain single covalent bond. So the same structural unit is the presence of the single covalent bond in all alkanes. Number 4 is called but and ane is for alkane. Similarly, pent means 5 and hex means 6. So to start off with, alkane is the simplest organic compound. All of the compounds seen in the right hand side of this table called methane, ethane, propane, butane, pentane and hexane, they belong to the same family and the family is called alkane. While drawing the structural formula of organic compounds, always keep this in the mind that the carbon is having a valency of 4. It means that carbon makes 4 single covalent bonds, nitrogen can make 3 single covalent bonds, oxygen can make 2 single covalent bonds, and hydrogen can make only 1 single covalent bond. To start off the understanding of alkenes, alkenes always contain a double covalent bond. If there are 2 covalent bonds between carbon atoms, then each carbon will just connect with 2 hydrogen atoms, and such a molecule is called as ethene. Eth means 2 and ene is the suffix used for all alkene molecules. Same is the case with alkynes. Wine means a triple covalent bond between two carbon atoms. So if we see a triple covalent bond, this is an alkyne. In an alkyne, each carbon is only linked with a single hydrogen atom as three of its valencies are fulfilled by the other carbon atom. So a hydrocarbon containing a triple covalent bond with two carbon atoms is called as ethine. So the alkyne is another family or a homologous series, and remember the members of each homologous series that differ from the next member by a common structural unit, usually CH2. It means that if you add CH2 to one member of the homologous series, you will get the next member. Similarly, adding CH2 to ethane, we will get C3H8, which is propane, which is the next member, and so on. Now we will look into the properties of the members of a homologous series. Before looking into the trends in the boiling points of the members of a particular homologous series, we'll take the example of alcohols. These are the compounds which contain hydroxyl or hydroxyl group, as it has been mentioned that the OH is attached to the carbon atom and the rest of the valencies of the carbon atom are fulfilled by the hydrogen atom by making single covalent bonds. A single carbon containing alkane is called as methane, and as it is containing OH, which is having a functional group called as alcohol, so the OL is used as a suffix which is going to replace the E in the methane at the end. So this compound is called as methanol. Similarly, an ethanol can be drawn by drawing two carbon atoms and attaching 6 hydrogen atoms by making single covalent bond and now replacing one of the hydrogen with hydroxyl group, so making an alcohol. This alcohol is called as ethanol. Like a 2 carbon compound is called as ethane and replacing the last E with the ol. So this is another homologous series. So we can have methanol containing 1 carbon atom, then ethanol containing 2 carbon atoms. And now predict the name of the third member of this series. Our propane is a hydrocarbon containing 3 carbon atoms, and this homologous series will be having the next member, propanol. So now we can see in this table the first 6 alcohol molecules are shown with their trivial names, molecular formula, boiling points, and solubility in water. Methyl alcohol is a common name, while its IUPAC, which is International Union of Pure and Applied Chemistry, that determines the rules to name organic compounds. The commonly called methyl alcohol, according to IUPAC, should be called as methanol. Similarly, ethyl alcohol, IUPAC name is ethanol. Similarly, propanol, N stands for normal, means it is neopropanol or a straight chain compound, which is a primary alcohol, which we will talk about later. Similarly, we have butanol, pentanol, and hexanol. Alcohols are taken over here as an example of the members of the homologous series to show the trend in the boiling point. As this could be seen, as the number of carbon atoms are increasing, the boiling point also keeps on increasing. As the carbon chain in the homologous series of any type of organic compound increases, the London dispersion forces of attraction also increase. So this increases the boiling point. So there is a direct relationship between the number of carbon atoms and the boiling point of the compounds in a homologous series. Moreover, these trends are true for all the straight chain compounds, but if there are branching in the compound, this is going to cause a decrease in the boiling point. For instance, if we take straight chain or normal pentyl alcohol or pentanol with the molecular formula C5H11OH with the boiling point 123.8 degrees Celsius, by drawing the structural formula of this compound, which is pentanol, or the IUPAC name is pentan-1-ol. If we compare this molecule with a branched compound having the OH attached to carbon number 1 and a branch is appearing at carbon atom number 3, we start numbering from the end which is close to the functional group which is OH or hydroxyl. Rest of the valencies should be fulfilled by hydrogen atoms. In order to name this compound, first of all, select the longest possible chain. Carbon atom number 3 is having a methyl attached with it. Methyl is a methane derivative, means a CH4 is methane, which has lost one of its hydrogen and attached with carbon atom number 3 as a branch. There are 4 carbon atoms in this chain, which is called as the stem chain, so it is a butane 1-ol. The molecular formula of 3-methyl butane 1-ol is C5H11OH, which is similar to pentane 1-ol. So these two compounds are called as isomers, which are having identical molecular formula but having different structures. Because of the branching, the molecule become more spherical in shape, which reduces the contact surface area between them and lowers the boiling point. So the boiling point of 3-methyl butane 1-ol will be much less than pentane 1-ol, which is around 87.2 degrees Celsius. In the next section, we are going to talk about different classes of organic compounds. First of all, the alkanes. As already discussed, ane means all the single covalent bonds are present. As mentioned earlier, they have a general formula of CnH2n plus 2. The first alkane is methane, which is containing 1 carbon atom attached with 4 hydrogen atoms by single covalent bonds, having the molecular formula CH4. The second member of this homologous series is C2H6, which is ethane, with a molecular formula of C2H6. This is ethane, and so on. Similarly, we have propane containing 3 carbon atoms and 8 hydrogen atoms. This compound is having the molecular formula C3H8 with the name propane. IB students only need to know the compounds up till 6 carbon atoms. Right now, we are seeing that how to draw a butane. This compound is called as butane, containing 4 carbon atoms and 10 hydrogen atoms. Number of hydrogen atoms can be calculated using the formula CnH2n plus 2, where n represents the number of carbon atoms in the respective alkane. Drawing the pentane with the 5 carbon atoms having 12 hydrogen atoms, 5 carbon containing compound is called as pent, and as it is an alkane, so the ane suffix will be used. So this is pentane with a molecular formula of C5H12, while the butane has the molecular formula C4H10. A 6 carbon containing alkane is called hexane with the molecular formula C6H14. All what we are talking about alkanes right now. So the methane is the first alkane or first member of this homologous series. Ethane C2H6 is the next one, and then we have propane C3H8, we have butane C4H10. You must do a practice of drawing all these structures. They seem quite simple while you're looking at on your computer or phone screen, but usually students do a mistake, especially with more complicated compounds. So the next class which we're going to talk about, they are alkenes. Alkenes are the compounds which are containing the general formula CnH2n, and ene is used as the suffix. A methene is not possible because a carbon cannot make a double covalent bond with hydrogen, so this cannot exist. So methane does not exist. The first alkene is the ethene, so erase the methane, which cannot exist. There should be only 2 hydrogen linking to each carbon in an ethene because there is a double covalent bond between the 2 carbon atoms. The molecular formula is C2H4, and the name of this compound is ethene, E-N-E, because there's a double covalent bond. The functional group is the double covalent bond. Functional group is that part of the molecule which is most reactive. Next member of alkene homologous series is C3H6. There should be a double covalent bond between any 2 carbon atoms, and these 2 carbon atoms have 1 hydrogen less than a normal propane. This compound is propene. Some students do a common sake, they think that double bond exists between all the carbon atoms in the alkenes. That is incorrect. A double bond cannot exist or cannot come between two consecutive carbon atoms. Next member of this homologous series alkene is butene with the molecular formula C4H8. There is a double covalent bond between carbon atom number 1 and 2. The numbering of the carbon should start from that end of the compound which is close to the functional group. It means that if numbering would start from the right side in this compound, that will be incorrect. So green set of numbers is incorrect according to International Union of Pure and Applied Chemistry rules. So this compound is butene, but it is important to mention the double bond, which is ene, is between carbon atom number 1 and carbon atom number 2. Whatever number is smaller, that is used. So the IUPAC name of this compound would be but-1-ene. There's a common question by students that could it be possible to have a double covalent bond between carbon atom number 2 and 3 as well as 1 and 2. I already have mentioned that this is not possible. There is a possibility of a double bond between carbon atom number 3 and 4 and 1 and 2 simultaneously. Such a compound could be named as but-1,3 diene. But such complicated structure is beyond the scope of IB. Now looking into pentene, we have to put a double bond. Let's say we are putting the double bond between carbon atom number 2 and 3. We should start numbering from the left side and the molecular formula is C5H10. The 2 hydrogen should be removed from this compound to keep the valency of carbon 4. Similarly, the hexene having a double bond somewhere in the middle of the compound, we are removing 1 hydrogen from both of the carbon atoms containing the double bond between them, resulting in the molecular formula of C6H12. According to IUPAC rule, we have to first number the carbon atoms. In this case, numbering can start from either end because the result would be the same. So the IUPAC name of this compound is hex-3-ene to mention the position of the double bond. Next compound which we are going to talk about now are alkynes. Alkynes are the hydrocarbons which contain a triple covalent bond. The general formula for alkynes is CnH2n-2. The first member is ethine, which is having a triple covalent bond between the 2 carbon atoms and having just 1 hydrogen attached to them, so it's C2H2. Similarly, our propyne is having the molecular formula C3H4. A butane with a molecular formula C4H6 having a triple covalent bond between carbon atom number 1 and carbon atom number 2. Its IUPAC name is but-1-wine or ine. Similarly, pent-2-wine or ine is C5H8 having the triple covalent bond between carbon atom number 2 and carbon atom number 3. Hexine with the molecular formula C6H10, IUPAC name is hex-3-1. Now we're going to talk about halogenoalkanes, and in order to understand halogenoalkanes, we have to bring all these molecules back into their ane configuration. Now all these compounds are back to alkanes, and as the name suggests, these are halogenoalkanes. It means that a halogen represented by X generally, which may include fluorine, chlorine, bromine, or iodine, may attach to any one or multiple carbon atoms in an alkane, turning it into a halogenoalkane. Let's say there is a bromine attached to carbon atom number 1 instead of a hydrogen, so it is called as ethyl bromide with a molecular formula of C2H5Br. Here ethyl is an ethane derivative which includes the part of the molecule which is left after the removal of 1 hydrogen, so C2H5. So basically an alkyl or alkanyl is a derivative of an alkane after the removal of 1 hydrogen. For example, methane can turn into a methyl group which can attach to any carbon atom in a chain. That's how we have got the ethyl bromide. It is commonly also written as bromoethane. Same is the case with the propane. If we replace, let's say, a chlorine with one of the 8 hydrogen atoms, we will get C3H7Cl, called as propyl chloride, which is the IUPAC name. But remember, over here the numbering is compulsory, and we must mention that the chlorine is attached to carbon atom number 3. But here comes the common mistake which students do. They start numbering always from the left side, which they have to be extremely careful. Numbering should begin from that end of the molecule, from where a functional group is starting or is closest. So in this particular case, the numbering should begin from the right side of the molecule, and this compound is called as propyl 1-chloride or 1-chloropropane. Similarly, if we attach an iodine with carbon atom number 2, the compound is called as but2-iodide or 2-iodobutane. And here we are seeing 1-bromohexane. And the pentane turns into pent3-chloride with the molecular formula C5H11Cl, having a chlorine attached to carbon atom number 3. Next homologous series which we are going to talk about is the alcohol. As we have seen that in an alkane, the halogen is attached to one or more carbon atoms, but in the case of alcohol, a hydroxyl group, as we have seen on the previous board as well. So in order to understand alcohols, we are going to replace all of the previously added halogens with the hydroxyl group. So the first member of this homologous series is named as ethanol. The respective ethane, the last alphabet E, is replaced by the ol from the alcohols. So name of this compound is ethanol with a molecular formula C2H5OH. Similarly, we get a propanol with C3H5OH, having the OH attached to carbon atom number 1. So here it is important to mention the position of ol. So we call it propan 1-ol because there are more possibilities over here. In the case of ethanol, there's no need to write ethan 1-ol. Hence, even if it attaches to a carbon atom number 2, then the carbon atom number 2 should become a carbon atom number 1, as the numbering should start from that end of the molecule which is close to the functional group. We can understand the butan 2-ol by looking at an OH attached to carbon atom number 2, mentioning the position of ol or OH. Similarly, a pentan 3-ol with a molecular formula C5H11OH. Molecular formula of butan 2-ol would be C4H9OH, and then we will get hexane 1-ol with the molecular formula C6H13OH. So the general formula of alcohols is CnH2n plus 1 and then OH. Now notice and cross-check all the molecular formulas on this board and try to find out one incorrect molecular formula deliberately written for you to point out. You can pause the video and check all the molecular formulas using the general formula for alcohols. And yes, the correct answer is all molecular formula are correct and there is no incorrect molecular formula. In order to understand ethers, first of all come to the section of the syllabus that deals with the identification of the typical functional groups. We already have talked about the alkyl groups. The alkyl group is shown by letter R, which is basically an alkane derivative. Alkane derivative means if we have a respective alkane, let's say we have a methane, and if we remove one hydrogen, so one of the valency of the carbon is free. So CH3 with one free valency of carbon is the alkyl group, sometimes also written as alkanyl group. So we got the methyl. Similarly, an ethyl will be C2H5 and one valency of the carbon is free, generally written as capital R. On the other hand, alkanyl group means if there is an alkene, so this alkenyl group is formed when a hydrogen is lost from one of the carbon atoms. This is called as methenyl group with a molecular formula C2H3, one valency free. Similarly, the alkynyl group is if we have an alkyne with a triple covalent bond between the two carbon atoms. If this compound loses one of the hydrogen, it will turn into C2H and one valency of the carbon is free. This is known as ethynyl group. So ethynyl means a double covalent bond, while vinyl group means there is a triple covalent bond. So this is the identification of the functional groups, going back to the next class of the organic compounds which we are going to learn, which includes all the ethers. Ethers are simple compounds having an alkyl group attached to an oxygen from one end and having another R group or alkyl group attached to another end. For example, if we have a CH3 linked to another CH3 with an oxygen, and the nomenclature include this is a methyl group. So this is meth and this is oxygen. So this is methoxymethane. So usually the group attached first on the left side of the oxygen that is named with the oxygen, with the group on the right side as its full name as an alkane. For example, if we have a C2H5 linked to another C2H5, means we have two ethyl groups linked to each other through this oxygen. In this ether, we call it ethoxyethane. Remember that ethers are quite confusing with a quite similar name as ester, but esters are completely different, which we're going to see in a minute. So next compound is aldehyde. Before digging the aldehyde further, we have to move forward to look into the identification of another functional group, which is the carbonyl group. A carbonyl group is the functional group in which a carbon atom is bonded to an oxygen atom by a double covalent bond and rest of the two valencies are free. Such a group is called as carbonyl group, and this group is common in aldehydes, formaldehyde, and ketones. So going back to the aldehydes, we have learned that we have the carbonyl group, which is C double bond O, is attached to an R group from one end, and in the aldehydes, it is always a hydrogen attached to the carbon, which is doubly bonded with the oxygen. An example of an aldehyde, the simplest one is the CH3 linked to the carbon having the double bond oxygen and the hydrogen. As the rule of thumb, first of all, select the longest possible chain which contains two carbon atoms. A two carbon atom containing compound is eth, and the first group is ane, so it's ethane. But to name the compound, the last E is replaced with the Al from the aldehyde. So this will become ethanol. For practice, we can see another compound, C double bond O, and having a hydrogen over here attached to a CH2, which is further attached to a CH3. So longest possible chain is containing three carbon atoms. A three carbon atom compound is called as propane for alkanes, as it is not an alkane, so last E will be replaced by an Al, so it will become a propanol. We are talking about aldehydes right now, and if in the carbonyl group both of the valencies of the carbon are fulfilled by hydrogen, this is a unique compound which has no any further types. This is known as formaldehyde with a molecular formula CH2O. General formula for aldehydes is CnH2n plus 1 COH. Now we'll focus on the ketones. The ketones are the compounds which are having another R group attached with the carbon having a doubly bonded oxygen. So it means that the two R groups, which can be the same or could be different, attached to either side of this carbon atom. An example of a ketone is a methyl attached to both sides of the carbonyl group. According to IUPAC rule, first of all, count the number of carbon atoms in the longest possible chain. There are three carbon atoms, so it is a propane as an alkane to start off with the stem name, but as it is not an alkane, so last E will be replaced by ONE. So this 1 indicates a ketone, so the name of this compound will become propanone. Similarly, if either side of the carbon atom is attached with ethyl groups, the longest possible chain suggests that its name should be a pentanone. But a pentanone could have another isomer. There is a possibility that one side of the carbonyl group is having a methyl attached with it and the other side is having a propyl attached with it. In such case, the longest possible chain is suggesting the presence of 5 carbon atoms. So this is also a pentanone, but obviously pentanone A and pentanone B, they are completely different molecules. So according to IUPAC rule, we have to write down pentan-3-one, mentioning the position of the attachment of oxygen by a double bond. And here, this compound is pentan-2-one. Now we are going to focus on the next group of compounds, or the next class, which is the ester. Ester is the compound which is quite similar to the ketones, but in ester, there is an extra oxygen between one of the R group and carbon. So basically, the carbon links to an oxygen which further links to the second R group. So a modification in this compound can turn it into an ester. So this is turning it into an ester. The two oxygens joined to the carbon atom with one of the R groups is given the name O8 according to the number of carbon atoms present in O8 group. For example, this could be an ethane as containing 2 carbon atoms. This is called as an ethanoate. And the alkyl group attached to the oxygen is separately named, which is a methyl. So a complete name of this compound is methyl ethanoate. After modifying our next compound, this has turned into an ester. After counting the number of carbon atoms in the O8 part of this compound, it could be named as propanoate, as it is a propane if it was an alkane, and the last E is replaced by O8. And the group attached to the oxygen is separately named. So this is methyl propanoate. A modification of the third compound on the board will turn it into an ethyl ethanoate. Next group of compound, or the class of compound we are going to look into, is the carboxylic acid. The carboxylic acids are also quite similar to esters, which contain a hydrogen instead of the second R group attached to the oxygen, which is singly bonded or bonded with the carbon by a single covalent bond. So after doing slight modifications in the compounds which we already have drawn, we can understand the structure of carboxylic acid, and we will learn how to name them according to IUPAC rules. So putting a hydrogen next to the oxygen, this compound has turned into a carboxylic acid. Carboxylic acids use the suffix oic acid as a replacement of last E of the respective alkane. So depending upon the number of carbon atoms, the alkane is named and the E is replaced by oic acid. So the first example could be named as ethanoic acid. The next example is having 3 carbon atoms. So it is called as a propanoic acid. There's no need to number any carbon over here or to number the position of oic acid, because oic acid should always be the first one or the first carbon to number, because we always start numbering from that end which is close to the functional group. Now we are focusing to the amines. Amines are the compounds which contain a derivative of ammonia. Ammonia is NH3, and a derivative of ammonia means if NH3 has lost one of its hydrogen, so one of the valency of nitrogen is free now, which can link to an R group. So general formula for amine is RNH2 or CnH2n plus 1 NH2. A common example of amine is CH3, which is a methyl attached to NH2. This is named as methylamine or amine. Looking into another example, if an ethyl is attached to an amine, this compound is called as ethylamine. Amides are different than amines because amides contain a carbonyl group in which an amine is attached to one side of the carbon and an R group is attached on the other side of the carbon. General formula is CnH2n plus 1 CO and H2. A common example, just replacing the R with CH3, we get the simplest amide. According to IUPAC naming rules, we count the number of carbon atoms. 2 carbon atom is ethane, and replace the last E with amide. So the name of this compound is ethanamide. Taking another example for clarity, if there is an ethyl group attached on one end of the carbonyl group, the total number of carbon atoms will become 3. That's how this compound is called as propanamide. A common mistake students do by just counting number of carbon atoms 2 in such case, which is incorrect. The misconception is due to the fact that students think the amide group include this whole thing. That's why they should not count that carbon while they are naming it, but which is a very common error which should be avoided. Nitrile are the second last class of the compounds which we're going to talk about. Nitriles contain a nitrogen atom bonded to a carbon atom by a triple covalent bond and having an R group attached on one end. An example of the nitrile is a CH3 attached to the carbon, which is having a triple covalent bond with the nitrogen. According to IUPAC rule, the number of carbon atoms are counted, and 2 carbon atom containing compound is called as ethane. In nitriles, nothing is removed. This is called as ethane nitrile. To look into another example, this is another nitrile which is having 3 carbon atoms in this compound. So this is a propane nitrile. And the last but not the least are the arenes. Arenes are the compounds which are cyclic compounds, also known as aromatic compounds. The cyclic or aromatic compounds are the compounds in which the first carbon links to the last carbon, and the most common example and the simplest one is the benzene with the 3 double covalent bonds between alternative carbon atoms. The molecular formula of benzene is C6H6, and this functional group is also called as phenyl, which is benzene. So if there's a benzene molecule having one of its valency free due to the loss of a hydrogen, it will become a phenyl with the molecular formula C6H5, one valency of carbon free. Hydroxyl or hydroxyl is actually the name given to the OH, in which one oxygen is linked to only one hydrogen and its one valency is free, which can attach to any other compound, for example in alcohols or in carboxylic acids. Carbonyl is already discussed, and carboxyl means an hydroxyl group attached to the carbonyl group. Means if we have a carbonyl group and having a hydroxyl group attached at the one side of the carbon and the other side is free, that is called as a carboxyl group, also shortly written as COOH. Carboxamide group is the carbonyl group having an amide attached on one side of the carbon. That is the name of the functional group, which is same as the name of the class carboxamide. About the aldehyde, it's the same thing as we have talked about the aldehyde compounds, means a carbonyl group having an R group on one side and the hydrogen on the opposite side. Remember, formaldehyde is different than aldehyde, in which the carbonyl group is having hydrogen attached on both sides of the carbon. Next functional group which we're going to talk about is the ester. We already have talked about esters are the compounds which contain the carbonyl group having a doubly bonded oxygen with both sides of this carbon linked to an R group, which could be identical or different. This prime stands for a possibility of a different R group linked on both sides of the ester. Ether is also same as the name of the class. It is ROR. A prime indicates that a different R group can attach on both sides. Amine we already have talked about, an R group attached to an NH2. And nitrile is the carbon linked to the nitrogen by a triple covalent bond having an R group. Alkyl, alkenyl, and alkynyl groups are already discussed. It is very important to notice that the functional groups are the reactive parts of a molecule. Let's say there is a carbonyl group, oxygen being more electronegative, it is going to pull the electronic pair with a greater force towards itself, due to which this will become partially negative. This is making the negative pole in the molecule and can make a partial positive carbon atom, which can later end up in the formation of carbocation. So it is important to keep always this in the head, that the functional groups are the reactive parts of a molecule. The next part of the syllabus which we are going to talk about is for structural isomerism. We already have done several examples of structural isomers. Isomers are the compounds which are having the same molecular formula, but they have a different arrangement of atoms. For instance, C4H10 is the molecular formula of a compound, and we're going to see how many different isomers could be formed. First of all, just draw a straight chain simplest alkane. This is a normal butane or a simple butane without having any branches. If I draw a compound containing 3 carbon atoms in the chain, and let's say the central carbon atom is having a methyl group attached with it, completing the rest of the valencies of the carbon. This compound also has the molecular formula C4H10, but this compound is not a butane. According to the IUPAC rule, select the longest possible chain, and this compound is named as 2-methylpropane. So these two compounds are isomers of each other, as they have the same molecular formula, which is C4H10, but their structures are completely different and they're two different compounds. Another example of structural isomerism could be seen by looking into a molecule C4H8. First compound that could be drawn, straight chain molecule, let's say having the double bond in the carbon atom number 1 and 2, completing all the rest of the valencies. This one is C4H8. Name of this compound is but-1-ene. Another possibility is playing with the position of the double bond. If the double bond shifts to another position between carbon atom number 2 and carbon atom number 3, this compound is named as but-2-ene. Now notice that students sometimes do a common mistake. They think that they will keep on shifting to the double bond to the right, and then they will keep on getting a new compound each time they're doing this move, but then they forget the general principle of IUPAC naming, that whenever we select the longest possible chain, the next thing we should do is numbering the carbon atom, which should begin from that end of the straight chain of carbon atoms which is closer to the functional group. So using that rule, this is still the same compound as what we have written at number 1, which is but-1-ene. So this could not be one of our isomers. We can have some more possibilities for the same molecular formula, but of course this one is incorrect. Another possibility is draw a chain of 3 carbon atoms, put a double covalent bond, and then link a methyl to carbon atom number 2. That's how this is the third isomer of C4H8. For naming, always start off the selection with the longest possible chain. Selecting a wrong chain will end up in wrong naming. Why is this chain incorrect? Because you cannot skip the important functional group over here, which is the double bond or ene. Numbering should begin from the left side of the compound, and the double bond is between carbon atom number 1 and number 2, having the methyl attached as a branch. So this compound is 2-methylprop-1-ene. Another possibility is a cyclic compound, but that is beyond the scope of the IB. IB clearly suggests in the syllabus that isomers should only be discussed for the straight chain compounds and not the cyclic one. But if you look at this setup, this is also having the same molecular formula C4H8, but remember, this is not an alkene, this is a cyclobutane. Next part of the syllabus is about the saturated and unsaturated compounds. A simple concept: saturated compounds are the compounds which are fully saturated with hydrogen atoms. For instance, we have a propane, and this propane is containing the maximum possible hydrogen atoms present in the compound, which is 8, having 3 carbon atoms. So this is C3H8. On the other hand, an unsaturated compound is the compound which is having a double or a triple covalent bond. For instance, in this propene is containing 2 hydrogen atoms less than a propane. So this is C3H6, this is a propene, and a propyne would be even having 2 further hydrogen atoms less than a propene. Because of the presence of a triple covalent bond, the number of hydrogen atoms are reducing because the valency of carbon should remain 4. So the unsaturated compounds are the compounds which contain a double or triple covalent bond, and they are called unsaturated because they are not fully saturated with the hydrogen atoms. The hydrogen atoms are not the max in number for a specific number of carbon atom, let's say for the respective alkane. The alkane can have 8 hydrogen atoms. We can say it is fully saturated. This is the max number of hydrogen atoms are present in a propane, but a propene and propyne, they are having progressively less number of hydrogen atoms in them. The next compound which we are going to talk about is the benzene. It is an aromatic compound. Aromatic means it is a cyclic compound which is unsaturated as it is containing double bonds. Benzene is a hexagonal ring which is containing 3 double bonds. The position of these double bonds keeps on shifting by a process known as resonance. Resonance is a process in which the double bond shifts between carbon atom number 1 and 2 to carbon number 2 and 3, and so on. So we can have different resonating structures of benzene, which could be shown by a double-headed arrow, and a shift of the double bond can be shown by this diagram. These are not the only 2 resonating structures. There are a total of 5 resonating structures in which the double bond could be between carbon atom number 2 and 3, between 5 and 6, and 1 and 4. Similarly, 2 other structures are showing the double bond between 1 and 2, 3 and 6, and 4 and 5. And the last structure is showing the resonance between the carbon atom numbers 6 and 1, 2 and 5, and 3 and 4. So the IUPAC name of the benzene is cyclohexane 1,3,5-triene. But in reality, benzene is not this compound. Benzene is a compound in which the double bond is constantly shifting by resonance, and the electrons are delocalized, which keep on transferring from one position or from one carbon position to another carbon position. So all of these resonating structures are shown by the Kekule structure, which is a merger of all of these resonating structures, and these resonating structures are all shown by a circle in the center. So this circle is representing all of the delocalized electrons. So it makes the part of the TOK, the theory of knowledge, in which it is considered that the Kekule structure is actually an inspiration came from a dream. Kekule saw the atoms whirling and dancing before his eyes, and then eventually the atoms began to reassemble into long rows that seemed to move about in a snake-like motion. As he watched the snake dance, the vision progressed until the snake devoured its own tail. That's how Kekule proposed his famous structure to describe the benzene molecule. In the next part, we are going to review the structural formula could be represented in full or condensed format. For instance, if you write a propene, the full format of the propene will be writing down all the carbon atoms in a straight chain, drawing a double bond between the first carbon and the second carbon. First carbon is having 2 hydrogen attached to it, second carbon is having only 1 hydrogen, and the third carbon is having 3 hydrogen atoms linked to it. While the condensed format is the one in which carbon with 2 hydrogen bonded with it is written as CH2, then we show a double covalent bond with a CH ending at a CH3. Another example of a condensed format is CH3, then we are writing a CH2 whole bracket 3, and then we are writing an OH. This is actually a butane 1-ol. Sometimes a skeletal formula is also used. For example, writing the butane 1-ol, a skeletal formula is actually showing a 2-dimensional geometry of the molecule. Basically, the end and each pointed crest or trough is representing a carbon atom. which is linked to an OH. Let's talk about the difference between the empirical, molecular, and structural formulas. The empirical formula from topic 1, we know that it is the simplest whole number ratio. So the empirical formula for benzene, which is having the molecular formula C6H6, the simplest whole number ratio is CH, while the structural formula is showing the details of all the carbon atoms and the shape of the molecule with all the possible bonds, including hydrogen and carbon atoms. We can take another example of butene with a molecular formula of C4H8. The empirical formula would be CH2, that is the simplest whole number ratio, and the structural formula is showing the details of all the bonds and the atoms attached in their respective format. So this is butane to ene. So the empirical formula refers to the simplest whole number ratio, while as molecular formula is showing the actual ratio of all the atoms in a molecule, and the structural formula shows the structure of a molecule. Molecules could be shown with the help of the 3D models, which could be real or virtual models. Like this is a 3D model. These 3D models are also available in the form of different kits, in which it can be clearly seen that a carbon atom is shown by this black ball, which is actually having 4 holes, so it can connect to 4 other atoms. These plastic sticks are showing the covalent bonds. Each plastic stick shows a single covalent bond. The hydrogen can be identified by its ability to make just a single covalent bond, and the blue colored ball is showing the nitrogen, which is having a valency of 3. Now we are going to look into a more complex example of a model showing a complex molecule. We can see the double bonds between the carbon and oxygen atom, while the blue ball is indicating the nitrogen, the gray balls are carbon, red is oxygen, and the white are hydrogen atoms. Here is another 3D model which is showing more complex molecules. These models actually help to develop the understanding of the actual shape of the complex molecules. About the IUPAC rules, we already have discussed certain IUPAC rules while naming the compounds. Let's say we have to name a compound, and in this compound, the first and the foremost rule is the selection of the longest possible chain. You can pause the video over here and take your time to decide which chain you are going to select as the main chain, also known as the stem chain. The correct longest possible chain which should be selected is this one. If you select the chain shown in green, then you are skipping important functional groups like OH and Cl, which could not be named properly then. Selection of blue chain is going to cause another mistake of skipping the double bond or the ene, which is being skipped. So the correct selection is of the orange chain or orangish yellow chain. I'm going to delete all the rest which are incorrect and going to complete the molecule by putting the remaining hydrogen atoms to fulfill the valency of carbon atoms. So rule number 1 is selection of longest possible chain. Second rule is selection of the side from where the numbering should begin. Numbering should start from the side which is closest to an important functional group, which in this case is the double bond ene. So we have carbon number 4, 5, and 6. Now identify which other groups are attached with the main stem chain. These are called as branches. There are in total 5 branches attached to this molecule. 2 of them are identical. Both of these branches, which are identical, are ethyl. As there are 2, we should be calling them diethyl, and we should mention the number of carbon atoms. It's 3,4-diethyl. Carbon number 3 is having a bromo, so it's a 3-bromo. Carbon number 5 is having an ol, so it is a 5-ol. And carbon number 6 is having a chloro, so this is 6-chloro. All these branches should be written in an alphabetical order. So the first of all, we'll write down 3-bromo, 6-chloro, 3, 4-diethyl, 5-ol, hexa-1-ene, which is the name of this compound according to IUPAC rules. Now we are going to look into the primary, secondary and tertiary carbon atoms in halogenoalkanes and in alcohols. A primary carbon atom is the carbon atom which is attached only with one more carbon atom or with no any other carbon atom. For instance, the carbon atom number 1 over here is connected to only one more carbon in this halogenoalkane. So carbon atom number 1 is called as a primary carbon in the halogenoalkane, which is connected to maximum of one more carbon in a compound. A secondary halogenoalkane carbon atom attached to a halogen, which is further attached with two carbon atoms. So this is a secondary carbon. According to IUPAC rules, if we number the carbon atoms, this is carbon atom number 2. So carbon atom number 2 is basically a secondary carbon. Name of this compound would be 2-bromopropane. A tertiary carbon now can be easily predicted is actually a carbon having a halogen attached to it, and all the rest of the three valencies are connected to three carbon atoms. So the carbon atom number 2 in this compound is actually a tertiary carbon. According to IUPAC rules, select the longest possible chain, which could be this one or this one. Both are identical. Doesn't make a difference. Numbering can even begin from either side. The name of this compound is 2-bromo, 2-methyl-propane. The first compound is bromoethane. There is no need to mention one because there is not any other possibility. Same is the case with alcohols. In order to understand the primary, secondary and tertiary carbon in alcohols, the hydroxyl group is attached to a carbon which is further attached with only one carbon. Name of this compound is ethanol, while a secondary carbon is a carbon having the OH attached to it, is having two more carbon atoms linked to it. The name of this compound is propan-2-ol. A tertiary carbon will be a carbon to which the OH is attached in an alcohol, having three more carbon atoms linked to it. The name of this compound is 2-methyl-propan-2-ol. Similarly, the primary, secondary and tertiary nitrogen atoms in the amines or amines can also be identified. In a primary amine, the amino group, which is NH2, is connected to a carbon which is further attached with only one more carbon. Such a nitrogen is called as the primary nitrogen. On the other hand, the secondary nitrogen will be the nitrogen in an amine which is connected to a carbon which is attached with two more carbon atoms. So the nitrogen is considered to be the secondary nitrogen in this case, not carbon. The name of this compound is 2-aminopropane, while the compound containing primary nitrogen is aminoethane. There is no need to mention one. A tertiary nitrogen will be a nitrogen connected to a carbon which is further linked to three more carbon atoms. Such a nitrogen is called as the tertiary nitrogen. The name of this compound is 2-methyl-2-aminopropane. Next is that part of the syllabus in which we are going to talk about the structure of benzene using some physical and chemical evidences. First of all, the physical evidence proves that all of the bonds in the benzene are of equal length. It does not matter which bond or the bond between which carbon atom is being measured, with a value of 0.140 nanometer. This value is shorter than the bond length between the carbon to carbon single covalent bond, which is 0.154 nanometers, and longer than the carbon double covalent bond carbon, which is 0.134 nanometers. So this indicates that the bond length is shorter than the single bond, but it is longer than the double bond. This is the proof of the resonance, that actually the electrons are delocalized inside the benzene ring and then they pull all of the carbon atoms to an equal distance from each other. There are multiple chemical evidences which describe the benzene structure. One of them is the rate of hydrolysis in benzene is much slower as compared to the straight chain compounds. This is due to the fact that benzene is having resonating double covalent bonds. So the benzene does not get hydrolyzed very quickly. If we compare the enthalpy of hydrogenation of a cyclohexane with a single double covalent bond with the benzene with 3 double covalent bonds, the hydrogen can be added to a cyclohexene in the presence of the catalyst nickel at a temperature of 180 degrees Celsius. The hydrogen will be added by addition reaction with the value of enthalpy change of negative 120 kilojoules per mole. On the other hand, if the benzene is hydrogenated, the enthalpy change value would be negative 210 kilojoules per mole. If it is a simple case of 3 of these double covalent bonds, then the enthalpy change value should be negative 120 times 3 equal to 360 kilojoules per mole. But that is not the case with the benzene, and we get negative 210, which is determined experimentally. So there is a difference of 150 kilojoules per mole, which is due to the extra energy associated with the delocalization of the electrons. Moreover, benzene also does not undergo the addition reaction very easily. Instead, the benzene show the substitution reaction, which will be seen by the reaction of the benzene with bromine. Instead of making a 1,2-dibromobenzene, it just makes a bromobenzene, indicating that the double bond did not break and the addition reaction did not take place. And the reason of the double bond being more stable is due to resonance. Next part of the syllabus is about the international mindedness, which refers to a small proportion of the nations are controlling the world oil resources. The oil prices and the ability to extract and refine oil affects the economy of not only the country but all over the world. So there are many economical and political influences which play a very important role in shaping up the global politics and economic development. The countries establish their relationships with the other countries and develop likings and dislikings with certain nations depending upon the ability to extract oil, its transportation, extraction and storage. After extraction of the petroleum, as a result of fractional distillation, certain components of the petrol with different octane number or octane rating are obtained. The octane number or octane rating is a standard measure of how well a petrol engine or a gasoline engine is going to perform, either used in cars or in aircrafts. The octane ratings, they could be often varying very widely throughout the globe, and there's not any set pattern or rule which describe the meaning of certain octane numbers or ratings used by different gasoline refining companies, but a general idea could be taken from an increasing number of octane. For example, in this picture we are going from 87 to 91, and of course higher the octane number, better the performance of the engine would be. As even the name is suggesting, the one which is 87, that is regular, 88, 89 and 90 are different levels of plus, and 91 is premium. Have you seen any octane number greater than 91, like 95 in your surrounding? Some countries, they have very few number or range of octane available at different gasoline stations. For example, in Middle East, we can only see 91 and 95. So the next part is the continuity of the international mindedness, in which we are going to talk about the consequences of using the fossil fuels as the main source of energy. The important thing about the fossil fuel to remember, fossil fuels are non-renewable sources of energy, and not only as a matter of fact, they are going to diminish and finish eventually after certain specific time, but combustion of these fossil fuels, they also produce many pollutants as well as greenhouse gases which have an influence in global warming. What could be done to address this problem? We should switch to the renewable sources of energy, including the solar energy, hydel energy, wind energy, as well as atomic energy. Of course, the other forms of energy have their on pros and cons, but then a very delicate balance has to be maintained while we are switching from non-renewable sources of energy to renewable sources of energy, and we have to look for other alternatives and new advancements, and should work for more inventions, and should use machines which are more efficient and consuming less energy and giving us more output. So the question is this: is the coal, oil and natural gas, is it worth to keep burning them and consuming these fossil fuels to obtain energy, or how important it is for a nation to switch to renewable resources? We'll be continuing with the international mindedness, in which we have the biofuel and alcohols. The biofuel and alcohol, these could be the alternative fuels to gasoline or petrol as well as diesel. Why are they called biofuels? Because alcohols are generally produced during a process called as fermentation. The glucose is used as a fuel or source of energy during fermentation, and this fermentation is done with the help of microorganisms called as yeast, which is a type of a fungus, and eventually we will get ethanol along with the production of carbon dioxide. This ethanol is a good fuel. It can be combined with the gasoline to produce a new type of fuel called as gasohol. This gasohol has a higher efficiency and it produces or emits less greenhouse gases. So this could be a better alternative, which is also not very expensive. We will be continuing with the theory of knowledge, in which the word organic chemistry, it originates from a misconception that there is the presence of a vital force, and that vital force is important to explain the chemistry of life. For a very long span of time, it was believed that organic compounds can only be formed within the bodies of living things, because in order to make an organic compound from an inorganic compound, a special vital force is needed, which can never be available artificially in the laboratory. While this misconception or the wrong concept was disproved by Frederick Wöhler, who first time produced the organic compounds in the laboratory from the inorganic compounds. So in science, many times there are some false ideas and concepts. They are established and they remain there and believed for a long time, since they are disproved with the modern approach. The last part of the syllabus is about the theory of knowledge of the utilization of all of the products which we obtain from the fractional distillation. The products produced from all the components obtained after fractional distillation of petroleum is called as petrochemical component or petrochemicals. These petrochemicals include certain dyes, pesticides, herbicides, explosives, different types of soaps, cosmetics, synthetic scents, and flavorings. The important part is all of these things are necessities of life, and the lifestyle of this era could not be imagined without the use of all of these petrochemicals obtained from the fractional distillation of petroleum. Please don't forget to subscribe the channel, press the bell icon for the latest updates, and drop a comment or any questions in the comment section below. Thanks a ton for watching. Hope to see you again soon.